All right, let's dive in. Today, we're tackling firefighting hydraulics with your pick, Paul Spurgeon's Fire Service Hydraulics and Pump Operations.
Great choice.
Now, I know what you're thinking hydraulics. Sounds kind of technical, but trust me, it's way more interesting than you might think.
It really is. It's about strategy and science all wrapped up in one.
Exactly. So, before we get into the nitty gritty, like those firefighter equations, which I'll admit sound a little intimidating, let's start with the basics. Why water? What makes it so effective for putting out fires?
Well, at its core, it's all about thermodynamics. Water, you see, has this amazing ability to absorb heat, like an incredible amount.
Okay, so it's like a sponge soaking up the heat.
Exactly. It's about something called the latent heat of vaporization.
The what now? Latent heat of.
Vaporization. Think of it this way. You've got a pot of water on the stove, right? Getting it hot, that's just raising its temperature. But turning that whole pot into steam, whoa, that takes a huge amount of energy. That's the latent heat of vaporization.
So it's sucking the energy right out of the fire as it turns to steam.
Exactly.
Yeah.
And because it needs so much heat to turn into steam, it's crazy effective at cooling things down fast. It's not just about dousing the flames, it's about cutting off their energy supply.
Yeah, I never thought about it like that. That's wild. It's like 6 times more energy to turn it to steam.
Yeah, it's a lot.
So that's why water is the go-to but.
Yeah.
And I'm sure there's a but here. There's some downsides to using water too, right? It can't be all perfect.
You're absolutely right. Water has its quirks.
Like what? Fill me in.
Well, one thing that might surprise people is how heavy it is. Like really heavy. Think of it this way. A cubic foot of water.
You mean like a big old bucket?
Yeah, kinda.
Yeah.
Imagine a box about the size of, say, a milk crate that weighs over 62 pounds. It's like carrying around a small adult.
No way, that much. So every time those firefighters are wrestling a hose, it's like a whole workout too.
Exactly. And that weight, it impacts everything. The size of the hoses they use, the pressure needed from the pumps.
Right, because it's not just about how much water they have, but the force behind it.
Exactly. And it's not just the weight either. Water has high surface tension, it can freeze, and get this, it conducts electricity.
It does what? Electricity. Hold on. So if you spray water on an electrical fire, you're basically.
Yeah, you're taking a big risk. You could become part of the circuit. Not a good look. And we haven't even touched on how water reacts with certain chemicals or the fact that it's not always great at smothering certain types of fires.
Okay, hold on. Things just got a whole lot more complicated. So water has a dark side.
You could say that.
Man, who knew? This deep dive is way more interesting than I expected. But before we get into those complexities.
We need to understand how firefighters think about water. Which brings us to firefighting math.
Oh boy, firefighting math. All right, hit me, but go easy on me, okay? Firefighting math. Okay, I'm ready. What's the key to understanding these equations? Where do we even start?
Well, remember that cubic foot of water we talked about? The one that weighs like a small adult. That weight, about 62.5 pounds, it translates into force. And firefighters, they need to understand how that force works, especially when it's under pressure.
Because it's not just about how much water you have, it's about how much force you can apply with it, right?
Yeah.
And pressure is force spread over an area, like.
Exactly. Imagine this. You're stepping on a Lego brick barefoot. Ouch. Right, that's high pressure, concentrated on a tiny area. Now picture an elephant wearing snowshoes, stepping on that same Lego. The force is the same, but it's spread out.
Okay, I get the analogy. Less pressure because of the snowshoes, but how does that relate to, like, a fire hose?
Think of a fire hose as a vertical column of water, kind of like a portable water tower. The pump on the fire truck, it pushes water into that hose, creating pressure. And just like with our Lego example, the size of the hose, the area that water is pushing against, makes a big difference in how much pressure is generated.
So a narrower hose equals higher pressure.
You got it. And that brings us to what's often called the firefighter's equation.
Okay, hit me with it. The secret formula.
All right, here it is. Engine pressure, what the pump generates, equals nozzle pressure plus friction loss plus appliance loss plus elevation.
Wow, okay. That's a lot to keep track of in the middle of a fire.
It is, but each part makes sense when you break it down. Nozzle pressure, that's the force of the water coming out of the hose, the part that actually hits the fire. Friction loss, well, that's a big one. Remember our King to garden hose example?
Right, the water flow gets all choked off.
Exactly. It's like trying to push a shopping cart down a bumpy road, tons of resistance. The same thing happens inside a fire hose. The water, it's constantly rubbing against the inside, creating friction, reducing the pressure. The rougher the lining of the hose, the more bends in the hose, and of course, the longer the hose.
The more friction you get.
Exactly. Spurgeon even talks about how, like, the type of weave in the hose jacket can affect friction.
Wow. So even the hose itself is a factor. What about appliance loss? What is that exactly?
Same idea. Any valves, gauges, fittings, even something as simple as a hose connection, it creates friction. It all adds up. And remember those standpipe systems we mentioned, the built-in hydrants in bigger buildings.
Right, those are considered appliances too.
Exactly. They're a huge advantage. Imagine lugging hoses up like 20 flights of stairs.
Yeah.
But those pipes, they still create friction, just like any other hose.
So when firefighters connect to a standpipe, they're basically adding more length to the hose, increasing friction loss. Okay, that makes sense. But what about elevation? It can't always be about hoses on the ground, right?
You're right. Gravity plays a big role.
Yeah.
Think about it. Even if there were no hoses at all, just a single column of water, the higher you go, the more pressure you need just to overcome gravity and get that water up there.
So fighting a fire on the top floor of a skyscraper, that's a whole other calculation.
Absolutely. They might need pumps running at full blast just to combat the elevation. It all comes down to understanding these different factors and how they, play off of each other.
That's a lot of mental math for someone in the middle of a fire.
Yeah. That's why training is so crucial. They need to know these calculations like the back of their hand. But there are other tricks of the trade too, like strategically using different hose diameters.
You mean like those giant hoses I sometimes see on fire trucks?
Exactly. Using a larger diameter hose for the main part of what's called the hose lay, and then reducing to a smaller, more maneuverable hose near the fire that's way more efficient.
So it's not just about having enough water. It's about getting it to the right place with the right amount of force at the right time. It's like a high pressure puzzle.
Exactly. And that's why understanding the weight of water, the different types of pressure, and what increases or decreases friction is so important. It all feeds into that firefighter's equation we talked about.
This is blowing my mind. I never realized how much science and strategy went into something as, seemingly simple as spraying water on a fire.
Right. It's not just about brute force. It's about working smarter, not harder. And that brings us to those standpipe and sprinkler systems, which have their own set of interesting challenges and solutions.
So we've covered a lot of ground here. The basics of water, the pressures involved. We even tackled that firefighter's equation. But what about those built-in systems? Standpipes, sprinklers, those have got to be game changers, right?
They absolutely are. Especially in those larger structures, time is critical.
Right. Every second counts.
Exactly. And like we talked about, those systems are considered appliances, so firefighters are factoring that extra friction loss into their calculations.
Right, because even though those pipes are already in the building, they still create resistance. And there are different types of standpipe systems too, right? I remember Spurgeon mentioned class 1, class 2, and class 3. What's the difference?
Okay, so picture this. You're responding to a fire, but it's on, say, the 10th floor.
Oh, man.
Hauling hoses up all those stairs. Talk about a nightmare. That's where those standpipes come in. Class I systems, those are designed specifically for firefighters. Larger diameter pipes, higher pressure. Firefighters can connect their hoses directly to them.
So it's like having a fire hydrant already waiting on every floor. So much faster.
Exactly. Now, Class 2 systems, those are more for building occupants, for those crucial moments before the fire department arrives.
Trying to buy some time.
Exactly. They have smaller hoses, lower pressure. Think of it as a quick way to try and control, or at least contain the fire before it spreads.
Okay, makes sense. And class 3, that's like the combo, right? Best of both worlds.
You got it. Connections for both the firefighters' larger hoses and the smaller ones for building occupants. Provides flexibility, depending on the situation.
Smart. Having options is never a bad thing when you're dealing with fire. But what about sprinkler systems? Those seem even more complex. I remember reading about all the different types of sprinkler heads and how they're activated.
Sprinkler systems, they're fascinating. Think of them like these silent guardians, always on standby, just waiting.
Waiting for the alarm.
Exactly. And the beauty of them is in their simplicity. They're designed to activate quickly and automatically, often before a fire even has a chance to really get going.
Containing it early on makes a huge difference.
Absolutely. And they do this most often with either a fusible link, basically a small piece of metal that's designed to melt at a specific temperature, or a frangible bulb.
A frangible bulb.
Yeah, it's filled with a liquid that expands with heat. When the temperature gets high enough, boom, the sprinkler head activates, releasing a targeted spray of water.
And those sprinkler heads, they're color-coded, right? So firefighters know what temperature they'll activate at.
Exactly. A simple visual cue that tells them a lot about the system they're dealing with. Again, it all goes back to firefighters needing to understand all these tools, all these systems at their disposal so they can use them strategically.
Wow, this has been eye-opening. Who knew there was so much to learn about firefighting hydraulics? It's not just about water, it's about physics and strategy, even a bit of engineering.
It really is. It's a great reminder that even things that seem simple can be surprisingly complex and fascinating when you dig a little deeper.
So true. Next time I see a fire truck, I'm going to be picturing all these calculations happening behind the scenes. It's like they're conducting a symphony of water pressure, all in the name of safety.
It really is remarkable, a testament to their skill and dedication.
Well, there you have it, folks. A crash course in firefighting hydraulics. We hope you enjoyed this deep dive, maybe learned a thing or two along the way. Until next time, stay curious.